So when we look at data, we will often look at things and say, well, there's an outlier. And often in just like everyday language, that term is used to mean something, but what does it really mean? So for example, I just did a Google search of outlier, looked at the news. Sweden is an outlier in virus restrictions. 4 nations with very different approaches to the crisis. Coronavirus outliers. Sam Ehlinger's unfortunate statistical outlier. Don't squander the chance to shine as a COVID-19 outlier. So we have this idea of outliers throughout the news, but what does it really mean? As you have seen so much in our work, these terms have kind of common notions, or we think we have an understanding, but do we really know exactly what they mean? So I'd like to return to our data that we used in the average PowerPoint, and this is just Arizona through Georgia just because I stopped there. And here are the numbers of cases back on that date. Now you might look at this and think, well man, 1709, that's an outlier, California. Compared to all the others, it's pretty high. Or maybe Delaware, 56, maybe that's an outlier. But how do we really know? Well, an outlier is a piece of data that is in an abnormal distance from the other points. Now just pause there for a minute. Abnormal. Well, what makes something abnormal? That's pretty imprecise as a definition, because what one person might think, like that California thing, that is an abnormal distance. How do we know, though? It's a data that lies outside the other values. Well, how far outside? If you had Pinocchio in a class of children, the length of his nose compared to the other children would be an outlier, according to Statistics How To. But how do we know? Just because it looks different, we're going to label it outlier? No, there's a mathematical meaning behind it. So let me do a quick reminder. Here's our data from Arizona to Georgia and the COVID cases a week or so ago from the time of this being recorded. We have 56 on the low in Delaware. We have 1709 on the high in California. And of course, if we go smack dab in the middle, look, what I mean by middle is 1, 2, 3, 4, middle, 1, 2, 3, 4. There's 4 on either side, so 327 is known as the median. Then, if we consider the left side of the median and find something in the middle. Now, there is not a single number in the middle because there's 2 and 2. There's 4 numbers. So the middle, so there's 2 numbers, a middle, and 2 numbers, is actually the average of the 2 that are in the middle. So 56, 2 in the middle, 164. Take the average of the 2 in the middle, and that gives you the median on that lower half. We call that the first quarter, the first quartile. Likewise, in the upper half, there's 2 numbers in the middle, so we'll average them, get an 847, and that's our third quartile. So the first quarter of the numbers, and then really there's a second quarter of the numbers leading us to the quartile. Then there's a third quarter of the numbers leading us to the third quartile, and then the fourth quarter would be the last 2 numbers. So there are your quartiles. And then we have a minimum of 56, a maximum of 1709. And then you saw how to make a box and whisker plot, and I'd like to, I'm actually going to ask you in an assignment to go to this metachart.com. Not that it's the only one. I don't have any vested interest in it, but it is a really easy place to make nice box and whisker plots, as you can see. And so you look, here's the box and whisker plot. Here's that minimum of 56. Here's that first quartile of 134. Here's the median of 327. You can see it in the number line here. And then we jump pretty far away to the 847 and then whoo, all the way to 1709. But still remember, there's the 2 numbers here that are pretty tightly packed there, 56 to 116. And there's 2 numbers in here, 937 to 1709, that are just really spread out. So the length of the whiskers or the length of the pieces of the box are just how spread out are the numbers, not about how many there are. So first quartile, minimum, first quartile, median, third quartile, max. There's the box whisker plot. And one might say that the 1709 seems abnormally far away or unusual compared to the other numbers, but is it really an outlier? Well, there's a definition for outlier. Here it is. An outlier on the high side. Like if a number was too big abnormally, it would have to be too big according to this rule of thumb, we could say. Now this is just what statisticians have agreed upon as the definition for how high is too high and to therefore be called an outlier. You take the Q3 number, in our case 847, and you add 1.5 times the interquartile range. Now the inner quartile range is how far it is between the first and the third quartiles, the inner quartiles. So how far is it from that 134 to the 847? Take 1.5 of those distances. And if you add it to the third quartile, if you get a number bigger than or smaller than 1709, then 1709 is outside of that. Or on the low side, say there was a number in here that was like 2. Is that an outlier on the low side? Well, we would find out by taking the first quartile and subtracting 1.5 times that inner quartile range. So here's what it looks like visually. Let me grab my pen. So our third quartile is this 847, which is right here. If we go beyond 847, 1.5 copies of the inner quartile range, that's this thing right here. And if we get a number such that it's less than, say, that 1709, then and only then would 1709 be officially an outlier. Or if we take the first quartile, in our case that 134, and subtract 1.5 times the inner quartile range. If we got a number that was not as low as, say, 56, then the 56 could be an outlier. In other words, this is going to produce sort of like a low and a high boundary. And if any of our numbers fall less than the low side or more than the greater side, then and only then are they officially outliers. So let's see what happens in this case. So here is the data. So in our case, the interquartile range is that distance from 847 to 134. We subtract those two numbers and we see that there's a distance of 713 in between. There's 713 spaces in between 134 and 847. So to get the high side, we'll take our third quartile of 847 and we'll add 1.5 times that interquartile range. Now grab your phone or grab a calculator and see if you agree with my number here. But when you put those together, you get 1916. So 1916 is somewhere out in here. And so notice on the high side, we don't have any data points that go beyond 1916. We don't have an outlier. On the low side, we take our lower quartile, our 134, and subtract 1.5 times that 713 interquartile range. And we get a negative 935.5. I mean, negative 935 is way over here. And so we certainly don't have any numbers that are beyond negative 935. In fact, all of our data lie between that lower and that higher values. So we would say that there are no outliers officially in the data set. Now, that's the official computed official statistic called outlier. That's how we would know. And the only way you get an outlier is if you had a data value that was beyond the high or beyond the low side. The high and the low kind of give us a fence. And if our data falls inside the fence, there's no outliers. If any data point were to fall outside the fence, you have an outlier. That's the official word on outliers. All right, go give it a shot. You'll see the assignment. Go.